We're live.
Oh, that second page though was first sentence.
So, just to put up a reminder from last class, just at the end of last class, I was talking about energy flow and energy conservation based upon Maxwell's equations and the energy stored in the field. And where I ended up, and I didn't write the final equation, was this. But there's a quantity which we're going to define as, which he defined as the pointing vector. Actually, I don't know who named it, whether it was pointing or not. Which describes the energy flow in the fields, right? And we're going to, in the next class, that's why I had to erase what Professor Wilkie had up this class at Hurd. But in the next class, I'm going to talk about electromagnetic waves, and then this will have a special meaning, a particular meaning there. But the pointing vector exists even for static fields. And energy conservation gives us this relationship then, that in the absence of charge, of the actual motion of charge, right, the divergence of the pointing vector is the rate of change. I think there's a minus sign here, but I'm not positive, so I'll label it. All right. Divergence of the pointing vector gives us the energy flow out of a volume of space. Yes?
Wait, this is not done.
No.
And you repeat
Yes. I started something on Thursday, and I wanted to finish it before I went on. And, am I going to do a review today? I'm going to answer questions today. I'm not going to give you a power review. But there are several things I can tell you about the examination. With that question, I cut short some of what I was going to say and just make one sort of neat point, I think, which is that if I had a physical situation where I had a ring of charge, and then I put a magnetic field inside of this, contained inside the ring of charge. Originally I had the field there. And then I start changing the field. Let's say, it doesn't matter which way I change it, I just change the magnitude of the field, okay? Well, we already know that when I do that, what's going to happen is that I'm going to induce an EMF around the loop. Lenz's law is going to induce an EMF. So in the absence of other forces, if all I do is I've got a magnetic field here, and then I decrease the field, right? I'm going to generate an EMF actually in this direction. Let's say if it were a decreasing field. If it were a decreasing field, I generate an EMF in this direction, which causes these charges here to accelerate around the ring. So I've gone from a situation with a field and fixed charges to less field and charges spinning around the ring. Yeah?
Would the ring of charges get larger if they're not bound?
I'll bind them to the ring.
Okay.
Although, I don't know that they get larger. The only forces are acting.
Right.
Oh no, as soon as they start to move,
Yeah.
then there's going to be centripetal acceleration that needs to be applied in order to keep them going on the circle. So yes, the diameter of the ring would change if I didn't do anything else. So I'm going to fix them on the ring. Now I'm going to change the magnetic field. And the only point that I wanted to make here is that I've now got a situation where I have physical angular momentum. So I started out with a field, I decreased the field, I ended up getting physical angular momentum in this problem, okay? Where did the angular momentum come from? You actually know the answer to that. It's in the field. So just a simple static magnetic field has angular momentum. A simple static electric field has angular momentum. We're going to talk class after next, because next test you're going to have fun. Next exam you're going to have fun. I am ill. I didn't not sleep properly last night. So next class you're going to have an examination which will be fun for you. Or fun for me, at least.
I am scared.
After that class, we're going to return to electromagnetic fields, and I'm going to talk about electromagnetic fields propagating all by their lonesomes as waves. And we will then talk again about the angular momentum of those waves. But you don't actually need to have a traveling wave in order for the fields to have angular momentum. It's there. You can tell it's there just by the fact that I changed the field. When I changed the field, I accelerated charges. I think that's cool. All right. What else do I want to say? I was going to talk about momentum in general. I think not. I'll save that because it can get quite involved. And I'd be introducing a new tensor at that point. And I specifically did leave time at the end of the course to take up a buffer for, if I run a little bit long on a few things. I think I left 2 classes at the end as buffers. So we'll hold off on that. For the examination, I have already, beginning of the course, posted this list. I'll hold it out. See it? This list of the schedule for the course. And I will just comment that Class 9 was on energy stored in fields and capacitors. Class 10 was on the space-time interval and the Lorentz transformation, and how the Lorentz transformation leads to a field associated with current. That was the, let's say, the plausibility and physical argument for current moving down a wire, and that then if you shift the frame from which you view that current moving, you end up adding a new force, which is an additional electric field due to the density of charges changing. And then I introduced the idea of 4 vectors and tensors, but in particular we focused on the vector potential, the 4 vector potential, and the 4 current, which is just C charge plus the 3 vector currents, right? We then did some vector calculus in space-time, and I introduced the field tensor and the boost tensor, or the Lorentz tensor for transformation. And you had a quiz on that, which I'm in the midst of grading now. You could probably get it back either later today. No, not later today. Tomorrow morning, if you'd like it. And there's likely to be something on that on the exam. Yeah.
By tomorrow morning, do you mean afternoon since you've got lecture and then lab?
No, I'm going to grade it tonight, so it'll be available tomorrow at 10. It'll be available earlier. No, sorry, I just lied. It'll be available tomorrow at 9. From 9 to 10 for sure, because that's when I'm in my office. And then probably from around 11:30 onwards, because I'll be back in my office then. Anybody who wants I think it's the 5th quiz, what'd I just get back, 6?
Yes.
Yeah, and then it's quiz 5, you can get back tomorrow. What I intend to do tonight as well is to post, let's say, a roadmap for each of the quiz problems and a roadmap for each of the homework problems, so that I'm not posting solutions, but just here's the trick or here's the approach that you might use for addressing this problem. Okay, I will not post the solutions. So you may start harassing me with emails after 10 o'clock tonight if you haven't seen the solutions posted yet, the roadmaps posted yet. Okay? I will reserve the right to filter your emails into appropriate boxes.
Spam.
All right, then, once we had the magnetic field from the boost of the electric field, start with Coulomb's law, boost it. I think that's just unbelievable. But then you get this other field in another direction that acts at right angles to the original force. It's crazy. But you do it, you get this extra force, and we demonstrated the equivalence of the electric and magnetic fields. They just transform back and forth into one another based upon how you look at them. But then having done that, we reverted to, let's call it classical magnetostatics, where we just looked at what happens when we have currents of various types. And we looked at 3 approaches to solving those kinds of problems. One was integrating the field out directly using, or finding the field directly by integrating the currents using Biot-Savart. 2 was finding the vector potential, and 3 was using Ampere's law. Ampere's law simply follows, if you wish, you only want to write one thing down. Actually, for the whole course, you can pretty much write down the component version of Maxwell's equations, one line, and then you've got it all. But, yeah.
So, we don't have to solve a magnetic potential, right? Not
You mean a
not
scalar
vector, but
potential
scalar
problem.
potential.
I'm going to say no. It was sufficient that I pointed out to you that it could be done. But I'm not.
So no boundary value
In my
problems?
entire professional life, I have never done that with the magnetic scalar potential, other than in this class.
So no.
And I think once as a graduate student and once as an undergraduate. So I don't think there's any value.
So no boundary value problems.
Understanding how the boundaries come into a problem, yeah, and therefore no boundary value problems of the electric field style scalar potential boundary value problems, right? But knowing what the currents are at boundaries and knowing how B and H must relate to one another at boundaries in order to simplify problems, those are powerful tools. So boundary value in this, no differential equation, expansion, boundary value problems. Although I may have overstated what I just said in that I will very likely ask you to tell me the dipole moment of some distribution of current. Not quite as easy as the homework problem. Okay? And for those of you who weren't at the homework help session or didn't view it online, there was a really easy approach to the finding the dipole moment of that solenoid, which was just take the magnetization and integrate it throughout the volume. Done. And magnetization was constant, I think. Yeah. So it was volume times magnetization. Yeah, so no magnetic scalar potential, but perhaps magnetic vector potential.
Thank you.
As a direct solution by integration. Then we introduce the time-varying fields, the Faraday's law and Ampere-Maxwell law. And that was about it. Inductance and mutual inductance could be fair game. Displacement current could be fair game. I would keep those relatively simple, because I don't believe that you had a homework on those. Conservation laws will not be on the exam. Okay, I'm done for now. Yes.
Will we be able to, when will we be able to hear back from the, I guess, regrades from the first exam?
I know where they are. I'd like to be sort of optimistic and promising and say, oh yeah, I'll have those for you tomorrow too. But I know that things happen to completely steal my time. So I can promise you one thing, which would be the quiz grading, but I can't promise you the regrades. And it doesn't do you any good to have the regrades
No, I
anyway,
was just curious.
because it just distracts you from studying, and there's nothing you can do about it at this point because we're beyond the drop deadline. So, yeah,
Will your office hours this week be a review session?
yes, no. My office hours this week will be a question and answer session.
Okay,
I'm
just like that.
I'm not going to review all of the material.
Like you did for the last test.
I don't remember what I did for the last test. Did I actually review things?
Yes.
Wow.
You took an
But
entire
there's more
class
to
period and called it exam number 1 review.
Yeah,
You
okay.
posted the bunch of
I'm more tired today than I was then.
I think
And
last
so top-
week you actually said there was going to be a review session on Wednesday.
Yes, that's what I asked.
Yeah, I say things when I'm like making big plans and I make promises, and now I can tell you truthfully, that's not going to happen today. And I actually don't see much of a point in giving you, a buzz review, because I think that what's in the notes and what I've talked about is what you need to know. And the homework problems are examples of the sorts of things that I might ask you to do. Yeah. So and then I'm happy to answer questions, but going point by point through all the topics, no.
Oh, well, for the notes online, there's only 15 and 16 posted since class 8, which was the review. Are you going to post the other notes, or?
Really?
Yes. Only
Oh,
15.
my.
Yeah. 9 through 14 are not there.
No, I didn't know that. Yeah, I have them all.
Okay.
I know where they are. That'll be the first thing that I will try to remember to do.
Add them to your
So should we
review
spam you
of-
the emails?
If, let's say, if you don't see it there by 6 o'clock today, the notes, then start spamming. Yeah.
Okay. Did you ever decide on the curve at the end or curve as you go issue from last exam?
Yeah, I'm going to curve. I'm definitely going to curve. And I have, let's say, generated a tentative curve. And I do intend to curve each examination. And so that might be more interesting to George than actually the regrade, I think. And I'll tell you what it is after the next exam, because I can't remember what it is. But I tried to make sure there's like a formula that I used, but then there were a few people who probably, it depends upon what happens on the next exam, probably will be hurt by a curve. And so I want to make sure that those people are not hurt by a curve. So there may be some individual adjustments as opposed to dropping the lowest exam.
Basically, the chapters from the Albanian textbook that we should go over for this exam are 5 through 11, right? Because that's what we've covered.
Yes, but I seem to remember that chapter 5 is almost all special relativity phenomenology.
6.
What?
It's 6.
And 6?
No.
Or
Just
just 6? All right. So there's a chapter in there that's all phenomenology. and I'm not going to test you on phenomenology.
And 5 was
Special general.
5,
I'll test you on field transformations.
5 was calculus or was?
Oh,
or no,
5 was vector
No, 5
one
was
of them was-
capacitors. 5 was
What?
capacitors.
Okay, so 5 is, energy in electric fields,
Yes.
all right?
6 was special.
6 was the introduction to special relativity, and
7 was vector.
I mean, you should know that from quantum physics.
Yep.
I don't feel the need to test you explicitly on it. However, if some relationship just comes up as the result of the way that a question is asked, I don't exclude that possibility. So you should be familiar with chapter 6 because you should be familiar with chapter 6 from previous. But the details, the extent to which Ohanian went through, and I think he does a terrific job, but he went through the phenomenology and what it means in a deep sense, no. Okay. Then I think that 7 was probably vector calculus in
Space-time.
space-time. And again, that's something that you need to use, but I'm not going to be examining you specifically on it. My goal is, for you, is in your being able to find the fields in this frame and in that frame, for example. So what I'm asking you to do is somewhat more, let's say, mechanical or plug and chug than what the material in the text does. All right? I hope that's okay with you. Yeah, Adam.
Speaking of the vectors, the differences in the actual usage of covectors versus contra.
Don't worry.
Okay, and I understand the notation at the same time.
I'll allow Professor Roberge to dig into that with you. I assume that he does.
When he
Who's
does-
taking general relativity? Does he dig into that?
no, next year.
Oh, no, who
Yeah,
is
same.
taking it? Or took it? Or, it's now, right?
With Trincoli, yeah.
Yeah. Oh, it's not Roberge, it's Trincala. And he spent some time on that, no? Covariant contra, what?
Yes.
He may have, but you might not have. I know that he did because he came to me to ask for my notes on covariant and contravariant vectors because he found what Ohanian wrote in the general relativity book to be too dense. Yes, he did not like Napolitano's lasagna.
So cheesy.
Ha. Yeah.
But now speaking of 4 vectors in general, not with the Einsteinian notation,
Yeah.
would it be possible to go over maybe an example of where we can use that and how we use that in a problem?
Okay, I'll save that for Wednesday. You email me that you want me to do that, and I'll prepare something for Wednesday. It's very seldom that you'll actually see a college professor at RPI in front of you on drugs, but you're seeing it now.
I don't because I had an entire semester of scholar.
Should I edit that?
Yes.
He did say no drink before the
Problem is, I'm not sure how
I do recall
to.
that being said.
Don't bother. It's no big deal. I didn't say it, did I?
No.
It's certainly not true. I respect all of the other professors in the department. But, no, okay, yeah. Adele.
The stuff that we didn't have homework on, do you have any problems that you think are representative of it in the text?
Here's what's going to happen in the next couple of days.
Okay.
I'm going to finish writing the Physics 2 exam today. I was supposed to finish it this morning, but I will have it finished by 5 o'clock today. Right, that will be done.
And then you
I'll
will
turn
put.
my attention to writing the electromagnetic theory examination. Once I've done that, I'm going to look at it and go, ooh, I don't think I covered that. And either I'm going to drop it off the examination or I'm going to drop very heavy hints on Wednesday.
Okay.
Okay?
Come on
So,
Wednesday.
if you can't be there on Wednesday, you should view the posting, and Eli promises to post immediately after the session.
I will probably be having people pointing shotguns at my back saying, "You must post this now."
I mean, you can post it right away.
Huh?
Don't you think you post it right away?
I try to.
Okay,
I don't always, but
Jacob.
Multiple choice questions, should we expect something similar to what was on the first exam in terms of difficulty?
Yes, you should. So think carefully. Don't think it's the easy answer when you look at a multiple choice. Realize that some of those you don't know him, but Professor Napolitano is my standard for deep and clever multiple choice questions.
now you're scaring me.
Have you decided upon how many?
No,
Oh, okay.
I'm going to say 5. What I have last time.
Will the
5 will be a problem. 5 multiple choice for 25 points, something like that. Is that what it was last time?
20 points.
20.
Okay, then it'll be 20.
Professor,
Yeah.
will the multiple choice questions of this exam be similar to how they were last exam?
Wasn't that was just asked?
Source.
Wasn't that just asked?
The answer was yes.
Oh, okay. Well, I think we hear it.
Probably.
There was some, Adam again?
Is there any good simile between the H field and D field and E field and B fields when it comes to the boundary problems with like perpendicular to?
Yes, but I haven't gone there yet. I will soon. It won't be useful to you this time around. It will be useful next time when we have, well, I mean, we're going to be dealing soon with propagating electromagnetic waves incident upon interfaces. And at that point, then the simile between E and D and B and H now comes out. We can talk about perpendicular and parallel components of each of those fields. But you don't need it yet. I don't want you to think about it yet.
Okay, it was right in the middle of the text and I felt like, yeah.
Yes. Yeah, it's coming, but it's not here yet. Yeah.
I vaguely remember you talking about the H field having some sort of physical significance. Can you remind me
No.
of that?
Yes. The H field comes from the real charge currents.
But has no significance.
What?
But has no real significance.
But there is no actual a field that acts upon things that is the H field.
So it's
It's the B field that acts upon things, and it's the E field that acts upon things. H and D are both theoretical constructs that make calculations easier,
okay.
that could make calculations easier.
Professor, if
Yeah.
what you said is true, and I know it is, then why is the Poynting vector composed of the E field and the H field? One field that exists and one field that does not.
Well, there's a mu in there if you want.
It's traditional.
Tradition, yeah.
1776?
So it
Yes, I believe that is 1776.
There's a mu in there, yeah, in MKS.
Yeah, there's a play called 1776.
Yes, that
that is
It's
quoted.
E cross B over mu. Yeah.
No, Fiddler on the Roof.
So
It's from Fiddler on the Roof.
Can't wait for the Jackson part.
Okay? Okay. Shall we sit here for 2 more minutes while you try to think of things to ask? Or are you ready to leave?
So let's go over what you said you were gonna do. You said you were gonna finish both exams for 1-5, upload the lectures.
Wait.
You gonna write it down?
Yeah, good.
He was going to finish the physics 2 by 5, post the notes by 6.
So you're gonna finish both exams by 5.
No,
No.
just physics 2.
Just physics 2.
Physics 2 by 5, notes by 6, quizzes by 10.
Notes by 6.
And upload the roadmaps to the quizzes and
Roadmaps by 6. No, roadmaps by 6. No, let him do it.
Notes by 6.
Notes by 6.
Roadmaps by 10.
And quizzes by 10.
We have a serious question. You better be good, yeah.
If we were to, once again, compute integrals on this exam, would it be comparative to the integral that we had to compute on the last exam, which is fairly straightforward, something you could look up in Chalmers?
Yes.
Should we bring a